Swayam Prabha. Digital India. Educated India.
See, a rigid body can have both translation and rotation. In the last few classes, we had attached a non-rotating translating axis to the rigid body and analyzed relative motion. Using that knowledge, we also got the absolute velocity and absolute acceleration of certain key points in the body. Suppose I attach a rotating frame of reference to the rigid body, what are the advantages and what is it that I am able to measure easily and what is that I do not see. This is needed for you to solve another class of problems where rotating axis will be a natural choice for you to do the relative motion analysis. At the start of the course, we have looked at this cyclone, and this is in the northern hemisphere, and you find that this is rotating in anti-clockwise direction. Okay. And we saw the southern hemisphere, this is rotating in clockwise direction. See, for many problems of day to day importance, we have just considered Earth as a frame of reference. We felt everything is quite alright with the Earth, fine. We were not really considering whether the Earth is rotating or not. But when you observe some of these phenomena, unless you recognize that Earth is rotating, it may be rotating slow, but it matters in certain understanding of these phenomena. So, there is a need for using a rotating frame of reference in certain applications. And just observe this and also make a neat sketch. What I have is, I have a particle having a motion like this, and by some means, if you know what is the description of this motion, then I can use polar or intrinsic coordinates to evaluate the dynamical quantities. The question is, are you in a position to get an expression, and in this case it is possible because this is developed by us and the particle is experiencing a spiral, it moves spirally and the equation is given as r equal to r naught e power n theta. So, I have the motion described, and once the motion is described, I can use polar or intrinsic coordinates. See, in the case of statics, I said when I show you a load, I have always asked you to visualize how the load could have been applied. Because in a practical problem, you see only load application in a practical sense, which you have to model it for you to solve the problem. And you also learn better engineering if you visualize how the load has been applied. It is easy to say that the particle is given a spiral motion, but how do you give this motion? You must also have a via media to do that, is it not? And if you visualize that, that makes you a better engineer and you appreciate problems in dynamics better. And look at the second animation. What do you see here? Here I see the particle is moving in a spiral. Observe this closely. There are two things that you can observe. The first thing is the disk is rotating, that is visible, because you are not sitting on the disk and observing what is happening to the particle. You are standing outside and visualize, and the disk is rotating slowly. So, you are able to see the rotation of the disk as well as how the particle is moving now. You can say that the particle is steadily moving in this slot. And if you look at what is the difference between these two, I only made the animation. I made the disk to rotate in a synchronous fashion with the particle. I am not getting altogether a different picture in comprehending how this particle moves, and also if you say finally I want only a spiral motion of the particle for a given application, how a spiral motion can be achieved by having a rotating disk and have your particle to move linearly in the slot. Is the idea clear? So, in many engineering application what you will find is only an appropriate mechanism is given in which certain relative motions are easily comprehensible. Many of the problems that come in engineering, they are like that. Okay, we will also see one example a short while later. And in this case, suppose I have not given this motion as spiral, I have started with this, then you would say that I have a disk is rotating and a particle is moving in the slot steadily. That is what you have here. Disk rotates, the particle moves in the slot steadily. So, this is what it says. The path is not clearly specified. Suppose I have given only this problem without this picture. Only an appropriate mechanism is given in which certain relative motions are easily comprehensible, then use of rotating frame of reference is recommended. See, mind you, I am looking at this as an external observer from the top. I am not rotating with the disk. Suppose I rotate with the disk, what is it that I would observe? I would observe only the particle is moving in the slot steadily. I would not sense that I am rotating with the disk. It is a subtle point, and this is what happened. People were looking at cosmological happenings around the earth, and they were sitting on a rotating frame of reference. So, rotating frame of reference becomes so important for you to comprehend, for you to analyze another class of problems. So, look at this. The only difference between the two animations is, here the particle is having its path. The particle has again a similar path in this animation also. But what I have done is, I have made this disk to rotate synchronously with the particle. That is the only difference. If you look at, suppose I have a light emitting mechanism to the particle and I have a photographic film, and then I find out exposure of this light and find out what is the path. In both the cases, the particle would have only spiral motion. Fine. So, on the other hand, if I have to get spiral motion, I simply have a disk to rotate and make the particle to move. Both are achievable. I can make the particle to move linearly in many fashion. I can have a screw thread and then it moves over it. So, physically it is achievable. Okay, it is physically achievable. And look at another example. You know, there are many theme parks are coming up, and you have to be very careful before you select the theme park. See that it is well maintained, fine, and then he has used new equipment, not imported equipment which they discarded abroad and then they are setting up a park. And in all this you have nice joy rides. Okay. So, only the rotation of the main arm is shown, and what is given in the problem? This cabin is rotating about itself in addition to the main arm rotating. So, in a problem like this, I know only the relative motions easily. I know what is the speed of the motor that I have given it to the cockpit here, and that is fitted to this arm, and this arm is rotated, and people devise many such variations to give you sort of happiness. Okay. But from an engineering perspective, if you are designing a theme park ride, you are expected to calculate the accelerations a person who would experience when he sits in the cockpit and moves through it. it cannot exceed certain recommended levels given by organizations which do research on human safety. So, if I have to do that, I necessarily need a rotating frame of reference for me to start with and do the analysis. So, there is a class of problem that requires use of a rotating frame of reference. And what are the usual forms? I have given fixed axis like this. The simplest one is I have a rotating axis whose origin coincides with this. It makes your life very, very simple. The origins are coincident. So, the mathematics becomes lot more simpler. And I would like you to make a sketch. Please keep a note of it. And I have another possibility. I can have the axis collinear. I have them collinear, and I can have any rotation. I can have a clockwise rotation, I can have anti-clockwise rotation, I can also have the speed of rotation changed. That is why I have given all these possibilities, because normally you get a mental block. We solve only a few problems. Whatever we have done in this problem is what you anticipate. In order to remove that mental block, what I am trying to bring out is, here the axes are collinear. The axis can have a clockwise rotation, anti-clockwise rotation, as well as the speed can differ. It can also have acceleration, all that is possible. Then I have another possibility. I have these axes are parallel, and the most general one is what you have here. I have this axis is oriented at some angle to start with. And if I develop the equations for this, all the other things are easy for you to do, fine. And what I have is, I have the position vector. I have always used the position vector in green color, and I have also followed a discipline in labeling this fixed axis and rotating axis. Rotating axis is in pink color, and the stationary axis is a family of blue. I have used different types of blue later, but it is a family of blue. So, you can easily identify which is the fixed axis of reference and which is the rotating frame of reference. So, I call the frame of reference O, capital X and capital Y. I call that as inertial frame of reference, because that is fixed. And I have a rotating frame of reference which is labeled as BXY, and these X and Y are small. Okay. These are capitals and these are small. To emphasize that this is a rotating axis, I have shown that this is rotating. The origin of this rotating axis is labeled as capital B. And whatever the point that I have on the object, I put it as A, and I view this point from the rotating frame of reference by the position vector here. There is RB, which denotes the position vector of B with respect to the fixed reference. There is RA with respect to B, which is seen in the rotating frame of reference. And once I have a rotating frame of reference, I have to be cautious that the unit vectors are not going to remain same. They will change. To start with, I put this as Ex and Ey, and later on, to make our life simple in writing, I would simply replace it by small I and j. Do not confuse this with Cartesian coordinates I and j. You have to be very clear of that. I use the symbol mainly because it is convenient for us to handle, because we are going to handle it repeatedly. With the explicit understanding, this is for a rotating frame of reference, and you would attach that it will have I dot and j dot. You should not jump onto Cartesian coordinates and say I dot is 0 and j dot is 0, do not get confused. This is to write your equations faster and easier to print books with that. Okay. So, this rotating axis can have a angular velocity as well as angular acceleration. We are not putting any restriction on it. In some problems, you may have only angular velocity. In some problems, you will have both angular velocity and angular acceleration. We are not putting any restriction. We are only going to view with a rotating frame of reference. And the moment I bring in the rotating frame of reference, I must also bring in the variation of E dot. So, E dot x becomes omega E y and E dot y becomes minus omega E x, which could also be written down in a different fashion. And I have the position vector for the point A is given as R A, and you have the relative position vector is R A with respect to B. Make a neat sketch of this. I have an expression R A equal to R B plus R A with respect to B. So, I can write R B and then this I can write it as x E x plus y E y. So, when I differentiate, I would recognize E x dot will be there, E y dot will be there, but later on I would simply replace it by I and j for convenience, because it is again nomenclature which we use. In this chapter we will use it like this. So, in the context you interpret I and j differently. So, that is what I have said. So, when I go for this axis where I have used capital X and capital Y, I would use capital I and capital J as the unit vectors. When I use small x and small y for the rotating axis, for convenience we simply put it as I and j. Understand the word convenience. Every time I have to write E suffix x and then put a dot, all that takes time, and it is also very difficult to compose books with that, fine. So, I have the fixed axis as capital I and capital J, and mind you, if I express these quantities with respect to I j, you should recognize that these are different. So, I can have some quantities with respect to capital I, some quantities with respect to capital J. So, if I do any mathematical calculation, you must have one consistent reference axis to which you put all the unit vectors appropriately. When you solve problems, you will understand that statement better. And we have I dot equal to omega j and j dot equal to minus omega I. I can also write these quantities in a much better convenient fashion, and it is also very easy to remember. Can I write it differently as a cross product? When do I get omega j? Omega is also a vector. Suppose I have omega cross I automatically get omega j. Omega is the magnitude here, but when I use it as a vectorial quantity, I can put cross product. Omega cross I is nothing but omega j. So, I use this for all my mathematical simplification later. So, put this axis and recognize that these are the vectorial quantities. So, I have put the vector cross product, and then I dot is simply omega cross I and j dot is omega cross j, with an explicit understanding that we are in the chapter on rotating frame of reference. We would interpret I and j as unit vectors of the rotating frame for convenience. So, I have also replaced RA as RB plus XI plus YJ. Now, the idea is to get the velocity. Let me differentiate this and get the velocity. See, now mathematics is very well developed. So, when you follow the mathematics route, you will never make a mistake. But if you look at the development of these part of mechanics, people made observations in those days. So, based on observation, they developed the mathematics. They did not have mathematics to assist them. So, there was lot of discussion on what a person would observe when you sit in a rotating frame of reference. There were a lot of debates on that. So, we will also go through that from that perspective and see whether we could understand the concepts better. And you can write this straightforward. I have this RB dot plus XI dot plus YJ dot and X dot I plus Y dot J. And there are also multiple symbols people use to refer these quantities. And we have adopted Merriam. So, he uses the terminology vrel to denote X dot I plus Y dot J. We have already seen how I can write I dot and J dot. On that strength, I could replace this as omega cross R. It is very, very important to do this. And we have not done anything great. We have just applied the mathematics systematically step by step. So, what we have got? Suppose I sit in a rotating frame of reference and I know what is the angular velocity of that rotating frame of reference. If I observe the point A, I can write the velocity of A with respect to the fixed frame of reference as absolute velocity of B plus omega cross R plus vrel. And what is this vrel? How can we measure this vrel? Another interpretation to this is the velocity with respect to the frame of reference xy, and what you actually call as vrel is what is the velocity a person who is sitting on the rotating frame would observe. That is a better terminology. Is the idea clear? Please write this expression. It is not given in Merriam, but you should write this, and if you see some other books, they use this kind of symbolism. There are multiple symbolism you have in this context, and you have to understand it, what is best for you. So, what I have is this component of velocity is what one would observe if you are sitting in a rotating frame of reference. See, in this development, I have not really brought in a rigid body. I have just said I have a particle A which is moving in space, and then I view that from another particle B, which is where I have put a rotating frame of reference. Now, let us give a feel to this, how I can achieve this kind of motion. Let me put a rigid body to this in a particular fashion and then handle it. So, before I get into that, I make a caution. I have a rotating frame of reference which is oriented at an angle. I and j have to be expressed in terms of capital I or capital J, or capital I and capital J should be expressed in terms of I and j for you to do mathematical simplification. Do not rush to solve a problem, fine. So, I express all the vectors in common coordinate system before summing them, otherwise this expression has no meaning, because certain quantities I get it from rotating frame of reference. This quantity I get it from fixed frame of reference. As long as you have a coincident axis, we started the first one like that, okay. If you see the samples, you may not have to do anything, even when the axes are parallel or even when the axes are collinear, you have no problem. Only when they are inclined like this, in some problems you may require this also. In those problems you have to be careful in doing the mathematics, be sensitive to that. So, what I am going to do now is, I am going to visualize how this motion could be seen if I have a rigid body, okay. And my interest is I should be able to see certain quantities when I sit in the rigid body and rotate with it, okay. And we have also seen slotted members earlier. So, this is the kind of idea that I am going to bring in. So, I have a fixed frame of reference, please make a neat sketch of it. Like I have given a large segment here for you to write, for me to draw the pictures. You also apportion this, because we are going to build up the picture one after the other, okay. So, what I am going to have is, I am going to imagine a rigid body in the rotating frame of reference. I attach this point B to one corner of the rigid body. I have the point A. So, until this it is like what we have seen earlier. Now, I bring in, I have a rigid body and I have a slot in the rigid body in some fashion. I have shown some generic curve, it can have any shape depending on the problem context. I am trying to give a life to this, how this motion could be achieved in practice. Like in statics, I said visualize how the loading has been applied. If you say there is a concentrated moment acting, I need to attach an arm and then put a couple force system. Similar to that, I have a particle A moving like this, particle B moving like this, I give a life to this for clarity. And even before we start this, we have the expression VA is VB plus omega cross R plus vrel as given in Merriam. From another perspective, it is velocity with respect to xy. Because this is a fixed frame of reference, this is your absolute velocity, and I have this VB as absolute velocity of B with respect to this. See, in your non-rotating frame of reference, that is, you have non-rotating translating axis. If I say VA, I have VB plus VA with respect to B, fine. That VA with respect to B now has two components, omega cross R plus VA xy. Is the idea clear? This is what I am going to explain it from different perspectives. Certain perspectives it will be clear for some students, other perspective will be clearer for a larger class of students. Okay. Let us see what it is. Now, I have this point located at a distance S, and we know very well that this is rotating with respect with an angular velocity omega. And mind you, we have also learnt the concept of coincident points. It is a fictitious point, the point is not existent, okay. But we imagine on this slot a point P which is identical to point A at this point in time. And I have the path is denoted as a dotted line, and only when I sit in this frame of reference and move with it, I would be able to measure this. I would be able to get this VAXY or vrel, which is also labeled as velocity of A with respect to P. Is the idea clear? We have already seen when I had the particle freely moving, I was not recognizing that this is moving linearly in a slot. But when I make the disk with the slot to rotate synchronously with the particle, I could perceive, because the motions were slow, that the particle is moving linearly on the slot. extending that logic, suppose I move and rotate with the body here, I would perceive the point A to move on this slot, whichever the contour that it has, and tangential to path is your velocity direction, that is what you get it here, fine. And this is to sensitize that this is not a fixed frame of reference, it is a moving frame of reference. Only when it is a rotating frame, I am in a position to see and measure the component vrel or vaxy. I will repeat it, okay. I could see that some of you are not totally convinced, we will get back to it again. And I have also written down one more thing, I have put this as omega cross r, I have put a direction perpendicular to that. Suppose I imagine at point B, I attach a non-rotating translating axis. It could be again x and y or x prime y prime, which is non-rotating. Can I write this? Because I know any point on the rigid body will appear as if it is rotating with respect to the point. Then I can find out the relative velocity. Relative velocity is perpendicular to the direction. That I label it as Vp with respect to B. I can also calculate the magnitude as omega cross r. So, I rewrite this expression as Va equal to Vb plus Vpb plus Vap. This is what I have written it now. Then I can say Vb plus Vpb is simply Vp, where Vp is the absolute velocity of the fictitious point. Is the idea clear? See, my ultimate objective is to find out what are the quantities I get from a rotating frame of reference and what quantities I do not see. Both are my interest now. From a mathematical perspective, we have already got the correct expression what I would have to use when I use a rotating frame of reference attached to point B. Now, the question is, how do I rationalize these terms from a physical perspective? Vp is the absolute velocity of P, and we have looked at this velocity of Pb plus Vap, fine, and then I can write this as Va equal to Vb plus Va with respect to B, which is what I started with. I have an expression for velocity here. If I have an expression from a non-rotating translating axis, I would only have Va equal to Vb plus Va with respect to B. And what is that Va with respect to B? Is nothing but omega cross r plus Va xy. So, what is the difference between a translating axis and a rotating axis? That is nothing but omega cross r. The person sitting on the rotating frame misses this quantity. See, whenever I use something, there are advantages, there are also disadvantages. The advantage is a person sitting on the rotating frame would be able to observe and measure this Vaxy comfortably. He would be able to measure this comfortably, otherwise it is very difficult to do it. On the other hand, because he is rotating with the object, he does not recognize this. You have to have this in your expression when you want to do it, only then your mathematics will be correct. Okay. Let me go and explain it in steps. We will spend some time on it. This is the crux of rotating frame of reference. If you understand this, then doing acceleration is simple, the mathematics will help you and you can comprehend it better. So, I explain it in stages. I want to bring back your old memories. when I attach a non-rotating translating axis to a rigid body, I see every other point on the body rotates about it. You might have forgotten that. Okay. So, again bring back that old memories. If I attach a non-rotating axis, translating axis to a rigid body, I would see every other point to rotate about that point. Okay. This is one knowledge you have got. Another knowledge, what is it you have got independently? I had a concept of coincident point introduced in a very simple system, where I could figure out what is the motion of A and what is the motion of point B, and I said point A is coincident with point B. This is what I said. And we understood from the physical motion of this, the relative velocity will be along the slot. You got that idea earlier, isn't it? That you would see only when you rotate along with the slotted member. I would be able to see that from a coincident point perspective, fine. So, when I have a slot, when I have a member that is rotating, the knowledge you get from coincident point discussion is the relative velocity will be along the slot. Okay. This is what you have got. I could write in this problem VA equal to VB plus VA with respect to B. Now, we come back to this VAB is the velocity along the slot for an observer rotating with the slotted arm. Okay. Now, let us understand what is happening here. Okay. Now, let us see what I am going to look at. This is I am going to look at the fictitious point P. I know very well that this object rotates with an angular velocity omega. I can attach a non-rotating translating axis at B and see what happens to this point. Somehow I have to get VA with respect to P, that we get it from a rotating frame of reference. Okay. But if I want to do it for the point P, I would say that VB plus VPB plus VAP. Can you find out what is VPB? You can find out from your non-rotating translating axis attached to the rigid body. I can always say VPB is nothing but omega cross R, that I can confidently say. Is the idea clear? As our original problem demands VAP, I have also shown this. And we also have the knowledge that VAP is nothing but what is the velocity perceived in the rotating frame xy. That idea you get from the coincident point when we took a very simple problem of a slot. Okay. And this I write it as VP plus VAP, fine. Then let me go and see the whole again. Okay. This is nothing but what you had seen earlier. We are revisiting the same discussion again, and I have this, and if I have to get the velocity VAP, I can get it only when I sit and rotate with the object. Otherwise, I cannot measure VAP. If the problem statement gives this, then you do not have to do it. But if I have to get that, I have to rotate with it. But this I can visualize from a non-rotating axis attached to it. So, what we are trying to give is a physical meaning to an expression like this, which we got without any difficulty by applying the mathematics systematically. Getting the expression mathematically straightforward, but understanding it from a physical perspective is little complicated and little tricky. This is what I am trying to explain it to you to the extent possible. So, whenever it is convenient, you consider the axis xy as a rotating axis. Whenever it is convenient, you see that as a non-rotating translating axis, understand the term omega cross r from a non-rotating translating axis, measure the term vrel from a rotating axis. So, we give life to this, and finally, the message here is the discussion, the final message of the discussion is omega cross r is the difference between the relative velocity as measured from non-rotating and rotating axis. It is a caution that omega cross r, a person who is rotating with the object does not perceive this. That is the message. Okay, if you understand that this is the message, then you can handle it carefully. How do I comprehend what we discussed for the slotted member? When I take coincident point, what is the distance between point A and point P? When you say coincident, what is the value of r? That is 0. So, when I have omega cross r plus that, this becomes 0 and you see only the relative velocity. Is the idea clear? Okay. And this can be generalized. Okay. This result can be generalized. And before we go into that, we would also label this in a convenient fashion. Please write down step by step. I am going to label them. VA is the absolute velocity of A, and VB is the absolute velocity of origin of rotating frame. See, in this context, I have labeled it as B. In some other problem, it is labeled with some other symbol D or E or F. You should know how to apply it. So, this is nothing but coordinate velocity. Okay, VB is nothing but absolute velocity of origin of rotating frame. So, it is a better way of remembering the terms in this expression. And what is omega? Angular velocity of the rotating frame x comma y measured from the fixed frame. Usually, the problems are constructed and you are in a position to make that device only by attaching a motor. You know what is the rotation of the motor. So, you essentially get only the relative quantity. So, this is the angular velocity of the rotating frame. And what is r? R is the position vector of the point seen in the rotating frame of reference, measured from x comma y. You should know that this is small x comma y. You know, in some slides I have changed the font for you to easily write, because I am using a PowerPoint slides. I could show a distinction between a small x comma y and capital X comma y. They appear very similar. Okay. And vrel equal to VAP. I also said vrel is one type of nomenclature. A better nomenclature is velocity as measured in the rotating frame of reference x comma y. Here a person rotating with the object will measure only this component of velocity. That is not the absolute velocity. So, you have to have additional terms for you to get the absolute velocity. So, whatever the understanding that we have gained in this can be extended to any vector. Okay. So, only the rotational effect is considered. We are not looking at the translational part of it. I have two positions A and A prime, please make it, and this is different by an angle d beta. Okay. Time derivative of a vector in a rotating frame of reference is related to the fixed frame as follows. So, we are writing it in a very generic fashion. I have any vector v, it is not necessarily the velocity vector, it is put as, that is why it put with a capital B. It can have a component Vx and Vy, Vxi plus Vyj, and when you differentiate it, you get it like this. We have already done this for the position vector r. the same mathematics. And what we perceive this is, if I want to find out the time derivative of a vector in fixed frame of reference, I should know the time derivative of the vector in the rotating frame of reference plus omega cross v. This is the very important aspect. This a rotating frame of observer, if you do all the calculation based on your observation, that alone is not sufficient. Observation, you miss it, somebody has to tell you you have missed it, and you have to have that in your analysis. But mathematics are developed very well now. So, from a mathematical route you have no difficulty. When these concepts were developed, they were not having parallel development in mathematics. So, they had to bank on observation, and then people predicted that if you have a cannonball from a artillery, it will move, when you do it on a north, it will move eastward, so on and so forth. People figured it out from a different perspective, and ultimately again, as I said, many of the scientific development are killing each other, whether you like it or not. So, they were worried about this, fine. So, they had made observation, then they understood from a mathematics. Now, you have the advantage and luxury of mathematics to help you. So, whenever I have a rotating frame of reference, if I am getting the time derivative, if I have to do it for the fixed frame of reference, I must have the quantity omega cross v. This is also pictorially depicted in the next slide. Okay, so, this is v dot xy equal to v dot xy plus omega cross v. Here I have changed the font so that you can easily write in your handwriting. You can write this kind of a font. This for clarity I have written it like this, but in all the other slides I have put only the Arial font. So, let us look at what happens when a small movement takes place, d beta. I have this as an expression. When I graphically represent, I should recognize that this is rotating with an angular velocity omega. I denote this position as theta. So, omega is theta dot, and I have at this instant of time, see the vector in space is in space, there is no difficulty at all. I have a vector in space, I view it from different axes, then I have all this mathematical requirement. What happens to the vector can be perceived from different frames. Okay, when I do it from a fixed frame, I get the final expression. That is what we will use it for our later computations. So, I have this with respect to the rotating frame of reference. Suppose this is at an angle beta, and in a small interval of time, this has moved by a distance d beta, and the point has moved from A to A prime. I have given a kinematical representation for this. So, the vector magnitude changes as well as direction changes. Is the idea clear? Fine. So, what is the change in the magnitude? I have a small change in the magnitude. I have put that as dV, and change in the orientation would be perceived by a observer sitting in the rotating frame in one way, observer sitting in a fixed frame in a different manner. This is what you will have to appreciate, okay, because I have a fixed observer will see this at an angle gamma. So, it will go by an angle d gamma. It has gone by an angle d beta now. I will go for d beta, b d beta. And I have this. This is what the observer sitting in the rotating frame will observe as the change dV by dV xy. He has a component as a function of as a magnitude variation, as a orientation variation. In addition to this, a person sitting here would also see v d theta, and the final quantity that this person will observe is dv xy. So, this is the v prime. So, the take today is, if I have a time derivative with respect to a fixed frame of reference is equal to time derivative in rotating frame of reference plus omega cross v. In fact, we would exploit this when we want to derive the acceleration terms. And when you do that, without any difficulty, you will also get the Coriolis component of acceleration. No difficulty at all, but to understand it from a physical perspective, it took generations for people to do it. Okay. So, in this class, we have said that a rigid body has a translation as well as a rotation. In the previous chapters, we have looked at, if I attach a non-rotating translating axis, what do you perceive? Suppose I attach a rotating axis to a rigid body, what is that you perceive and what is that you do not perceive? Both are necessary, so that you can have a proper mathematics. And in a class of problems, use of rotating frame of reference is very elegant to solve. Thank you.